Okay, so just after calibration, I'll cover a bit of the convolution part as well. So here you can see on page 36, it talks about convolution. So Liang will probably cover this next week, and it won't come in your quiz, so don't worry about it. But let's try and understand it a bit, right? So a convolution is basically where you modify the pixels in an image based on some sort of function in a local neighborhood. Okay, so what that means is, let's say this is your image or part of your image, right? You have some sort of function that can kind of do something to these numbers and output another number, right? So as an example, let's take this, right? So this is a typical instance of some sort of convolution happening. So the symbol for a convolution operation is this, right? So convolution is actually a mathematical, it's kind of like multiplication, but you do it on larger grids and things like that, right? So for example, here, what you've done is you multiplied, so the convolution operation acts like this, right? You multiply each of this with this, right? So 10 into 0, 5 into 0, 3 into 0, 4 into 0, 0 0.5 into 5, 0 into 1, 0 into 1, 1 into 1, 0 0.5 into 7, right? And whatever that you get resulting of it, you add up and put it in the center, right? So let me show you what I mean by this, right? So if you multiply this into this, right, you will get um, I'll actually, hold on, let me try it here. So I'm just going to show you the output of the multiplication here, right? So if I multiply 10 into 0, I'll get 0 here. If I multiply 5 into 0 here, I'll get 0 here. If I multiply 3 into 0, I'll get 0 here. 4 into 0, 0. 0 0.5 into 5 is 2.5. That's a 2. 1 into 0 is 0. 1 into 0 is 0. 1 into 1 is 1. And then I have 7 into 0 0.5 is 3.5. Right. That's the result of the multiplication. But this is not just multiplication, it's convolution. So on top of multiplying, you then need to add all of this up, right? So if I add 2.5 to 3.5, you get 6. 6 plus 1 is 7. And then that's how you get this 7 here, right? So you multiply and then add. Cool. So convolution is not just this. If you have a larger grid of images, right? So this is a section of the grid. You need to take this is what you multiply with is called the kernel, right? So this is the kernel. So you take this kernel and you slide it along the entire image, right? And you get the values that you get here. So that's basically what convolution is. So convolution can do very interesting things, right? For example, you can blur images through convolution. So what you do is you take this kernel, right? So this kernel right here is a 3x3 grid. You apply it to a section of your image like this and do the operation that I just explained. You multiply and then you add everything up and you select and you put one value there, right? So if you do that here and then you slide this kernel all over this image, right? What you get is you can blur an image, for example, right? So depending on the kernel, you'll have different effects on an image, right? So for example, these are a couple of examples of kernels, right, that you can multiply with. If you multiply with the identity kernel, you get the input image and the output image will be pretty much the same, right? But if you do multiply it with these kernels, you can get like, you can do an edge detection, for example, right? You can understand why you can get an edge, for example, by looking at these values that you're multiplying with, right? So what's happening here is your kind of, uh, when you multiply with this, what you're doing is you're actually finding the edges of an image here, right? If you really think about it, you can try it out on numbers and actually see it happen, right? So if you multiply using these kernels, you can get like an edge image like this. You can sharpen the image by multiplying using this. So what you're doing here is you're doing your, if you really look at it, for each middle pixel, you're increasing that value by 5, right? Which is why you get sharper edges, right? So you can spend some time here and look at these kernels and really think about what it does to the numbers in a grid, right? So I'll let you guys experiment with that yourselves. Just take a piece of paper, right? Look at some values of a grid, on numbers on a grid, and then try this convolution operation and look at what actually happens to the numbers. When you look at what happens to the numbers, you can get an idea of why these effects end up happening on an image, right? So you can apply what we call a Gaussian blur. So anyone who's used Photoshop or Illustrator or whatever to kind of sharpen an image, or even like your Instagram apps where you have like, when you're editing your photo, you can like sharpen it, blur it, and all that stuff. What you're doing is some sort of convolution with these kernels, right? So that's basically what the convolution operation is. Again, like you can try this activity. You'll probably do this in next week's class. And when you multiply this out, you can, and carry out convolution, you can see how it really affects an image, what it does to places with high intensity, like here, what it does to the highest intensity pixels, what it does to the lowest intensity pixels, things like that. And then you can get a feel for how convolution really affects an image. Is that clear? Does anyone want me to go a bit more into convolution, or you'll learn this in more detail in next class and get to do these activities as well? But that's the gist of it. You take what we call a kernel like this, and you basically do this. You multiply and you add, and you do it to the whole image. Okay, so let's see how we can do that in MATLAB, right? So basically, if you look at the question, yeah, so luckily in MATLAB, right, you have a function called convol with kernel, right, which is what I'm going to teach you guys now, right, which makes things super useful. You don't have to do the multiplication and is there a formula to determine the output matrix, the size? Okay, so actually what we do in this tutorial, give me a sec, is, okay, so actually what you have to do first is you have to write your own function on how to do it, right? So I'll just show you guys an example of the answer, right? All right, sorry. So you don't have to do it. We are going to use the MATLAB function. Okay, so MATLAB, if you type help conv2, right, you can see that there's an inbuilt MATLAB function that does the convolution, right? It does 2D convolution between two matrices, right? So what we're going to do is we're just going to use that function. So you have an input image and a kernel. And so to answer your question about the image size, this convolution function can, if you look at the help here, it says, it gives you a couple of options, right, about the shape, about the final size, right? Which is a good question. Like, how do you determine what happens to the ultimate size, right? So for example, here, if you look at this, you can see that these pixels end up empty, right? So what happens there? So what usually happens, the image size actually reduces, right? When you do some sort of convolution. But to avoid that, there are techniques. Like one technique, for example, is you do something called padding, where you kind of add like additional padding around this to make sure that the shape is not affected. Like you guys don't have to worry about that too much, because what we're going to do is we're going to use MATLAB's inbuilt convolution function to do this, right? So in MATLAB's inbuilt convolution function, if you say help conv2, you get an option about how you want the final size to be, right? So you need to put your input image, the kernel, and then this option of how you want the shape and size of your final output to be, right? So these are the three options that you have. You have full, right? So this returns the full 2D convolution, right? So that is if you pad it out, and actually you can play around with this and see how these affect it. So the option that I picked is same, right? So what that does is it returns an output that's the same size of the input image, right? And then valid is it returns only those parts of the convolution that are computed with the zero padding edges, right? So you guys don't have to worry about things like padding and stuff like that, right? All you need to know at this stage is convolution can process your image uh, in particular ways depending on your kernel, right? So it can either blur image, sharpen an image, right, and find the edges on an image, things like that, right? So for example, let's say in your projects you need to detect edges and things like that, right? You can just add a like you can convolve with a kernel and easily get the image pixels out of it. Okay, so you don't have to worry about things like padding and stuff. If you use the option same in this function, you should get an output image that's the same, right? So I've written my own function here, right, just like last week, and I'm going to call it convolve with kernel. I input an image, I input a kernel, and then the output image, I'm just using the MATLAB inbuilt function conv2. I'm putting this input image, the kernel, and I'm using the same option, which would give me the same size of your input image, right? And then I'm casting into uint8. We did that last week as well, just to make sure everything is in the range of 0 to 256. And then I'm using the imshow function to show the result. Okay, any questions with this function? Okay, no. So now what I'm going to do is I'm going to try different types of convolutions, right? I'm going to read, I provided 3 images, right? The Sydney Harbour Bridge image, the Opera House, and an ultrasound image, right? So what you've been asked to do in this question is sharpen the Sydney Harbour Bridge image, detect edges in the Opera House image, and apply a Gaussian blur to the ultrasound image, right? So what you need to do is use the function that we just wrote and the list of kernels that are there in your slides, right? And pick the appropriate kernel and do the convolution and see what it does to the image. Okay, so I'll give you like 5 minutes to try that out. So if you want, I'll put that function back up so you guys can see how to write the function. So I'll leave this up here. So you write this function, and then you can call this function in another script and define the kernel, read an image, put that image as the input image, and the kernel as your, and pick the kernel from your slides and put it into this function, right? One small note, your input image will have to be converted into grayscale before doing this, because we are applying convolution on a 2D grid, not a 2D by 3 grid, right? If you have a RGB image, you have a 2D grid on a 2D grid on a 2D grid. But if you have a grayscale image, you just have one grid, right? So we are doing convolution on a 2D grayscale image. So convert to grayscale first. You can use MATLAB's inbuilt functions to do that. So can you guys try this question for the next 5 minutes? Okay, so I'm just gonna do the question. So you guys, I'll put up all these codes so you can review them again along with the recordings. Right, so what we need to do is first we need to read the image, right? So we did this last week. You use imread, right? And I'm reading it into a variable called I, right? I'm going to, before running this, also run a clear all and close all to make sure that everything is cleared, all the variables that I had before. And then I'm going to convert to grayscale. So remember, MATLAB has an inbuilt function to do that. So it's just RGB to gray. I input this image. And then the first question says we need to apply some sort of sharpening to the image, right? So if you look at the list of kernels that we have, the sharpened kernel looks something like this, right? So I'm going to define the kernel like this, right? So it's just a simple MATLAB matrix with basically the same values that are there on your slide. Cool. Okay, so I've defined the kernel, and then I'm going to call that convolution function that we did before, right? So what you need for that is basically the grayscale image, which I just got from this line of code, and then the kernel that I just defined here. And then when I run it, I get the image result, which is my output. And then this set of code just shows you the images that I've created here: the initial original image, the grayscale image, and the final result. So if I run this, I should get 3 images, right? So this is the original image, right? This is the grayscale. This is the grayscale, right? And this is the sharpen operation. Hold on. This is the sharpened operation. You can see the difference, right? You can see this is much more. The edges and stuff have become sharper, right? Did everyone manage to do this? Is anyone having trouble with it? Okay, awesome. If you do have issues, just mention it in the chat. Okay, so that is your sharpening operation. And then for the second image, you've been asked to, where is that? Yeah, sorry. In the second image, you've been asked to detect edges. So you pick a kernel for edge detection. So I'm going to use this. So all I have to do is here in the kernel definition, I change it to 1, 0, 0, 0, 0, 0, -1, 0, 1. Okay. -1, 0, 1, and the image should be the Opera House image. Okay. So I change the image here to so when I run this should now detect edges in the image. Right, so this is the original image, grayscale image, and the edges, right? So you can try the different kernels here and see how intense the edge detection becomes, right? So we can try this, for example, -1, -1, and 8. Let's try that out. So if I run this, grayscale, and this is the edge detection, right? So you can see that it's more drastic. So you can play around with these kernels and see how they really affect it. All you're essentially doing is taking a grid and doing that matrix operation called convolution on it, right? So, and you can see that yeah, yeah, it's good that we're not getting to do this by hand. But on a small image, you should be also able to do it by hand. Like it's just a multiplication, addition, multiplication, addition. But yeah, it's pretty convenient that we can do all of this in code. But yeah, so that's that. And then you can try the third one as well, which is just basically you do the same thing, but you need to sharpen this ultrasound, sorry, apply a blur on the ultrasound image. So you load the ultrasound image that we provided and then pick the right kernel. You get the idea. It's the same kind of thing you need to do. Okay, so the last question number 3, is basically using Ross's USB cam node, right? So How many of you guys have used Rust before? Like, have you, do you guys know what Rust is? Okay, so have you guys set up Rust on your computers? Okay, used it before. Okay, so a couple of things that you guys can do this week. Okay, that's fine. Don't worry about it. Okay. Okay, cool, awesome. So couple of things you can do this week. I think it's time that all of you install Ubuntu on your systems, right? And I would suggest not using a VMware because it can get really annoying, especially when you start your projects. If you want to, you can continue on your VMwares, but trust me, it's just going to be super annoying, especially in the last minute when you're trying to do a lot of things. Like it's just going to be a nightmare, right? So that initial investment you put into dual booting your laptop with Ubuntu is going to be super helpful with your projects, right? And I'm telling you guys all of this based off of experience teaching 2 other batches, right? So take it for what it is. Try and set up a dual boot system. It'll be super helpful. Yeah, so Ubuntu versions and Rust versions you could use. I suggest using Ubuntu 18.04, right? It's fairly stable now and considered the what we call LTS, which is like long-term support. So Ubuntu 18.04, and along with it, the Rust version that you can use is Rust Melodic, right? So if you want to know how to install Rust, just type Rust Melodic installation, right? And it should give you a set of instructions, right? So read through these instructions carefully, and all you have to do is copy paste these instructions, right? They're fairly straightforward. So the first step that you need to do is set up Ubuntu, and then the second step is install Rust on Ubuntu. Okay, it should be fine. Yeah, shouldn't be a problem, but it's starting to get outdated now. Like, I mean, if you want, you can use 16.04 and Kinetic. But if you're thinking long term now, I think like the support for Kinetic and Ubuntu 16.4 is being phased out. So if you guys want, I'm guessing you guys want to do robotics in the next couple of years as well. So might as well use the upgraded versions. About a year ago, the upgraded versions were not that great. They were not that stable, but now I've been using it for my research and they're fairly stable. And you hardly have to deal with any issues. So I think setting up 18.04 and Melodic might make sense, just in terms of like long-term use. But yeah, so on top of that, you on this Rust website, there's some really great tutorials, right? So you can see here Rust tutorials. If you're having trouble with Rust, there is the beginner level tutorials. If you do these few tutorials, right, you should have more than enough knowledge on Rust, right? And they're fairly easy and straightforward, right? On top of this, there's also plenty of YouTube videos and things like that. Just remember, initially it might be a bit annoying, right? Because you're kind of learning a new skill. But Rust honestly makes things super easy, right? You will realize that when you get into projects, because you're dealing with interfacing with robots, interfacing with different systems, different computers, networking, and Rust actually saves you a lot of time. It does all the heavy lifting for you, right? For example, on my PhD project, um, I have a NVIDIA uh, Jetson running, which uses it doesn't use a it uses a completely different like process architecture, and then I have an upboard Intel upboard running, which uses completely different processor architecture, and then I have an Android tablet running separately, and I have connected everything through ROS. And I don't know how I would have been able to do it if ROS didn't exist, right? So ROS provides this really great ability to network across different systems and communicate with sensors really easily. So initially it might be slightly, because it's something completely new, it might be slightly difficult to grasp, but stick with it and run through the tutorials and you'll get the hang of it, right? What are the problems that could occur from using VMs such as VirtualBox? So it's very difficult to boot into Linux if you have a Mac, so wouldn't really have a choice. I haven't really dual booted with a Mac before, so I'm not really sure how difficult it would be, but there are many people who do that. Yeah, exactly. So there's quite a few problems with the VMwares. One thing, they're really slow. So especially since, okay, so another thing I want to tell you guys, maybe Liang covered this as well. Your projects will most probably be in simulation form this time, right? Because we won't have time. We like because of the quarantine situation. I don't think you guys will be able to play around too much with hardware. But ROS has a really great simulation environment, right, called Gazebo. So most of what you will be doing in your projects will probably be using simulation, right? So from ROS's perspective, it doesn't care whether it's an actual robot or a simulated robot, right? Everything you write on ROS or MATLAB using ROS you'll be able to plug into a hardware very easily, right? It doesn't know the difference between a simulation or a hardware, right? So everything that you do in your project, although you'll be running it on the simulation, you should be able to easily run it on hardware as well, right? But since we can't really uh, play around with hardware too much, we'll be doing everything in simulation. But the downside of simulation is you need, like, it's going to tax your computer's memory and things like that. And if you're going to run simulations on a VMware, it's going to be a complete nightmare because it's going to be really slow and you're going to have a lot of trouble. So try and dual boot your systems is the best advice I can give you. You have about 3 more weeks before your project starts. So take like a day and try to figure it out, because once you figure it out once, it becomes easy. And you need to learn that process of like troubleshooting, running into problems. Like it's all part of the process, right? Like that's how you learn. Like even the first time I played around with Linux or set up ROS, like I ran into a ton of problems, but it teaches you how to read through documentation, find how to like troubleshoot problems, right? Like all of that is part of the process, especially in robotics, because you'll be playing a lot with software, you'll be playing a lot with like hardware, and you're always going to have like problems. And so it comes with the game, right? So what kind of computer do I have and the specs, right? So the great thing about Ubuntu and ROS and things like that, they run on very low computing requirements, right? So Linux is generally faster on any computer compared to say Windows and iOS, right? Mac, right? So um, right now, so I actually have like 4 separate computers. Like I have my uni computer, which is like a Dell with a Core i7, 16 GB RAM. It's not that like powerful. Then I also have a powerful computer to do like deep learning stuff on. But then the computer that I'm running my research project on, which is a robot, has very low computing power, right? So for example, the turtle bots that you would have been using just run Raspberry Pis on them, right? Which don't have that much specs on them. But if you're running a simulation on your laptop should be good enough to run simulations. But I don't think it'll be practical to run it on a VMware because VMwares are already pretty slow. So try to set up some sort of dual boot system. You do it once, you should be like you run into problems, but troubleshoot them and try and figure them out. If you have a lot of issues, you can always email me and I'll try to like help you guys out with it as well, right? But that initial pain and like the trouble you go through in setting it up, like it's an essential like rite of passage for any robotics student, I think, because you need to, these are like basic essential skills that you'll need. Because when you're working with robots a lot, you will end up having to install Ubuntu multiple times, right, on different computers and things like that. So it's a skill that you might as well acquire now itself, right? So spend this week, take a day, make sure you don't destroy your, like back up all your data before you try it. Because if you end up accidentally destroying your Windows system, make sure you have a backup of your data, because you might, just make sure you don't do that. For example, when you're installing Linux, make sure you have a separate partition for Linux and install it on that partition and not on your Windows partition. Because if you install it on your Windows partition, you might format it accidentally and destroy all your data. So before starting, make sure you back up your files. But it's something that you should, I think at this point, like try and set up. And then set up ROS. Spend this week trying to do that. Because then once the projects start, it'll be easier. Okay, so I'll actually do the last, yeah. If I have 2 hard drives and I install Linux on the other one, do I need to back up both? If you have any critical data, just back it up anyway, because if you accidentally install it on the wrong hard drive or something like that, you're going to regret it. So like, yeah, just make sure if it's on the same computer. The thing is, like, if everything goes right, you don't have to back up your data at all, because if you pick the right partition, if you pick the right hard drive and you install it to that, nothing's going to happen to your Windows. It's going to be completely fine. But if you accidentally make a mistake and install it on the wrong partition, on the wrong hard drive, you're screwed, right? Yes. Yes. Just partition, or if you have a completely empty hard drive that you just want Linux on it, just install it on that. There's also a third option where you can install it onto an external hard drive, right? But then usually it's best if you have a really fast hard drive, like a M2 or a SATA hard drive, like a SSD or something. Then you can install it on an external hard drive. But yeah. Any other questions with Linux and ROS? Okay, so I think I'll end it at that, since even there's plenty of issues. Like sometimes, like there's different types of BIOS systems as well. There's something called UEFI and legacy. You need to check all this stuff. Usually any sort of instruction on dual booting online should run through everything. Yeah. So if you can help each other out as well, if you're really struggling, but usually the instructions online are pretty clear, and if you follow them properly, you should be fine. But in case you're really struggling, you can ask a friend or you can ask me, and I'll try my best to help out. So I won't do the third question today because you guys haven't set up ROS and stuff, and I'll do that next week. Yes, we should. I'll talk to Liang and try and create an official Microsoft Teams group for everyone, and I'll update you guys. So basically, in today's tutorial, especially for tomorrow's quiz, question 1 is super important, right? And understanding how camera projections work. So things you need to understand, just read up on camera projections, really understand the geometry. It's not complicated at all. All you need is like high school math to understand trigonometry, right? So spend some time reading how like a pinhole camera module works, and all those equations will be easy to understand. And then know how to do a camera calibration using this toolbox, and how to write the projection equations. I'll re-record that first question with a short explanation about camera projection as well, and I'll upload it hopefully by tonight. And then the third question about the ROS camera node, we'll do that next week, but I want you guys to set up ROS on your computers by next week, so we can actually it'll be easier for you guys if you can follow along with me, right? So I'm going to assume that you guys will have ROS set up by next week. So this question itself gives you the links. If you see here, it says installing and configuring ROS environment. There's a link here. You can follow it. Okay, so I would just say just question 1, camera calibration. Sure, I mean, just look at question number 1. That's all I can tell you guys. If you want, I can just re-mention that down UTS online. But really, just go through question number 1 again and try and really understand how each of the what you're doing in each of the steps, right? So what can really help you is the initial link I provided here in the tutorial, this camera calibration toolbox or MATLAB page, right? Read through this, look at the first calibration example, right? Read through it and practice it a few times and be ready for the quiz, right? But yeah, just I think question number 1 should really be your focus today's tutorial. Any other questions? Okay, thanks for sticking around till 2 o'clock. I'm really sorry about the Zoom issue. Again, it's a classic example of what happens when you're dealing with pieces of software. And like I said before, you need to, you trust me, you'll face those kind of issues multiplied by 100 times when you're dealing with actual robots, and worse when you're dealing with code that you wrote yourself, right? Which is, yeah, which is quite problematic. So if you're ever kind of feeling frustrated, don't let it get you down. Just keep going, keep troubleshooting, keep trying to find answers. And that's basically the learning process when it comes to robotics, like making mistakes, screwing up, learning, and trying again, right? It's something that we all go through. So sorry if the class was a little hectic as well. I had to rush through a lot of material. Hopefully I'll re-record everything in a much more slow. I'm not really sure if he did. I'll talk to him and see. Yeah, hopefully he did. Yeah. Okay, thanks for joining. Next week, hopefully things. Okay, he did. Okay, awesome. Hopefully things will go much more smoother next week. It will go much more smoother next week now that we all have understood some of the shortcomings. And I'll try to create the Microsoft Teams so that everyone can kind of collaborate, ask questions, and deal with the issues. All right, guys. Thanks a lot. Hope everyone's staying safe.